All right. So greetings, YouTube. Beautiful mind here. We're going to be continuing our discussion on derivatives. We're continuing chapter 3 on applications of differentiation, and we're moving into section 3.6, marginals, differentials, and linearization. So some objectives here are we want to find the marginal cost, revenue, and profit. We want to find delta y and dy. We want to use differentials for approximations. We want to find the linearization of a function at x equals a. So given C of x, R of x, and P of x represent respectively the total cost, revenue, and profit from the production and sale of x items, the marginal cost at x is given by C prime of x. Is going to be the approximate cost of the x minus the first item. So C prime is going to be, let me see. So the derivative is going to be basically it's like y2 minus y1. Okay, so it's an approximation. And then if we were to solve for the C of x plus 1, so the C of x plus first term is going to be C of x plus the derivative. Again, this is approximation, so this is close. This isn't exact here, okay? The marginal revenue at x given by r prime is the approximate revenue from the x plus first item. So then r prime is approximately r of x plus 1 minus r of x. So it's still kind of like the y sub 2 minus y sub 1. And this is similar for the marginal profit. Okay. So given this cost function and this revenue function, we're asked to find each of the following: the total profit, total cost, revenue, and profit from the production and sale of 50 units, the marginal cost, revenue, and profit when 50 units are produced and sold. Okay. Let me add a page. I want to get this one to go before we look at the notes. Let's see. Let me get a copy of this cost function and revenue function. Guess we can get the whole thing. Okay. We're just going to kind of have it here for reference. And let's actually do the following. Give me just a moment. Okay. So then for part A, the total profit, right? So profit in this context is going to be what? Revenue minus cost, right? So the profit is going to be the difference basically between your revenue and your cost. Okay. So then that's going to be this minus, I'm going to get all this on one line. Let's make that a little bit cleaner because that kind of looked like an 8. I think that's it, right? So then let's do okay. So then if we were to distribute this negative, I'm going to distribute and go ahead and try to combine like terms as best I can. So I think there's no like term with the x cubed. We got negative 12x squared minus 62. Was it negative 74? 40x, there's no like term with that one. 10 minus 27,500 is what? Negative 27,490. Okay. And that's our profit function. Okay, I think that's fine. So I'm just going to box that. I'm going to put that in a box. Okay. And then let's go ahead and that was part A. Let's do part B. the total cost, revenue, and profit from the production and sale of 50 units. Okay, so then basically they're asking a C of 50. So then basically a calculator, 62 times 50 squared plus 27,500. Okay, R 50 is going to be 50 cubed minus 12 times 50 squared plus 40 times 50 plus 10. And then the profit, we can just subtract those results. Okay. Let's do this. C of 50. I'm going to use Siri, so I'm going to have to, I'm going to talk it out. So just bear with me. Hey Siri, what's 62 times 50 times 50 plus 27,500?
62 times 50 times
Nope.
50 plus 27 is 155,027.
Let me do it right here. I just need like that. All right.
The answer
Okay.
is 182,500.
182,500. Okay. Now for this revenue. Hey Siri, what's 50 times 50 times 50 minus 12 times 50 times 50 plus 40 times 50 plus 10?
50 times 50 times 50 minus 12 times 50 times 50 plus 40 times 50 plus 10 is 97,010.
Let me check that because that something don't seem right there. You got 12 times 50 times 50 plus 40 times 50 plus 10. Revenue minus costs, all right? I mean, I guess this could be the case. So we got 97,010. And that's the revenue generated from the production and sale of 50 items. So then we're in the red, right? The profit here. Hey Siri, what's 97,010 minus 182,500?
97,010 minus 182,500 is negative 85,490.
Okay. I mean, that could be the case. I'm going to go with it for now. You know, you usually don't want that, but that could be the case. So we're going to let that be. Let me just put this in a box. And actually, let me do this real quick. I just wanted this all to fit on one page. So like if you guys were to print this, it won't be spilling over to a second page. Let me do one other thing. All right, that looks good. Okay. All right, I'll go with this for now. That's just the numbers, you know, provided we crunch the numbers properly. The marginal cost. So what do we say? It's basically your change in Y. So marginal cost, revenue, and profit. And it's, do they want the exact or an approximation? I mean, if we just use the formula that we just had, okay, let's use what we just brought up. So then C prime, when we produce and sell 50 units, it should be is it the 51st? Minus, it's basically like Y2 minus Y1. Okay, so I'm thinking it's gonna be, I'm just gonna glance. I'm having a little bit of a brain fog right here. Oh, so they're just using the derivative? Okay. Okay, we can just use the derivative then. Cost function, I think I can use that line. Let's kind of, where's my cost function? Okay, it's a little bit up there. What is that? 144x. So that's going to be 144 times 50. Is that right? 60 and 60 is 120. 124. Hey Siri, what's 124 times 50?
124 times 50 is 6,200.
Okay. The marginal revenue. So if we're looking at the revenue function, it's going to be, and we take the derivative, it's going to be what? 3 times 50 squared minus 24 times 50 plus 40. Okay. Hey Siri, what's 3 times 50 times 50 minus 24 times 50 plus 40?
3 times 50 times 50 minus 24 times 50 plus 40 is 6,340.
I feel like maybe we did something wrong. Let me look at it again. Let me recalculate that revenue. Hey Siri, what's 50 times 50 times 50 minus 12 times 50 times 50 plus 40 times 50 plus 10?
50 times 50
Yeah.
times 50
Okay.
minus 12 times 50
I'm gonna
times
just
50
go with
plus
it.
40
And
times 50
then
plus 10
the
is
marginal
77 minus
profit.
10.
So P prime. Let me see. I want to say we should, will that be the same or not? Let's use the derivative. So that's going to be 3 times 50 squared 148 minus 148 times 50 plus 40. Wait a minute. Revenue, uh-oh. I think I may have used the wrong revenue function. Let me look at it again. R 3x squared minus 24. Okay, I think we're okay. Let's keep going with it. And the profit function. So we brought the 3 down to the power of 1 plus 40. All right, okay. Hey Siri, what's 3 times 50 times 50 minus 148 times 50 plus 40?
3 times 50 times 50 minus 148 times 50 plus 40 is 140.
Okay, let's paste. Let's shrink this down. Copy. Come on. Nope. Undo. Undo. Yeah. All right. Let's compare this with the type, the notes that were prepared in advance. Okay. Something seems off. But let's go with it and let's kind of glance and see what it's looking like. Okay, let's do like this. Okay. So now for A, we got this long expression. 27,490, 40. Okay, I think we're okay. And then B, 182. Yeah, 85,490 in the red. Okay, so that's good. And then I think these are all okay. So when 50 units have been made, the approximate cost of the 51st unit will be 6,200. Okay, and the approximate revenue from the sale of the 51st unit will be 6,340 for an approximate profit on the 51st unit of 140. Okay, so I guess it's confirming that we should turn a profit. What's like? Well, let's not go into all of that just yet. Okay, I think that was kind of interesting. Let's keep going. So for y equals this, x equals this, and this, find the change in y. Let's see. Okay, I'm just gonna kind of do this one with brute force, right? Change in y is like y2 minus y1. So like I'm gonna kind of deviate from. I'm just gonna kind of do it on the fly, right? So if I change in y, so the second y, Let me think. It's basically going to be, okay. So it's like, I'm gonna write it like this. It's like, it's essentially y2 minus y1, right? And so the second y is gonna come from basically 4 plus 0.01, right? So that's gonna be 4 plus 0.1 squared minus the first y, which is just gonna be 4 squared. And then we should be able to get a number there. Hey Siri, what's 4.01? Nope, cancel. What's 4.1 times 4.1 minus 16? Okay. This is the result that I got. So the change in y, this is delta y, this symbol. This means the change in y from y2 to y1. Let's see how do we do. Okay, so we got 0.81, and you see it there. So yeah, I was tempted to change the y to f of x, and then you could say f of x plus. So this delta x is like a change, some small change in x, right? So a change in y is going to be basically the second y minus the first y. So then you saw where we did basically this line, and then we got the same result. Okay, let's keep going. I'm going to leave this as an exercise for you. Okay, so we have differentials and delta notation. For f, a continuous differentiable function, and small changes in x, f prime, the derivative is going to be approximated by basically the slope, the change in y over change in x. So remember, the derivative is going to be the slope of a tangent line at a point. And so then for small changes in x, the slope of the tangent line at a point is approximated by the slope between 2 points, where those points are like close to the original point, where the second point is close to the original. So again, the slope of the tangent line at a point can be approximated by the slope between 2 points, where that second point is really close to the first point. And then if we solve for the delta y, basically by multiplying both sides by delta x, then we get delta y equals f prime times, or is approximated by f prime times delta x, okay? So we're asked to, I think I'm gonna just use the notes here, approximate the square root of 27 using that delta y is approximately f prime times delta x. So we're gonna let f of x be the square root of x, and we're gonna let x be a number close to 27, so we're gonna let x be 25. So then the change in x is gonna be 2, right? Okay, so then the derivative here, the 1/2 comes down, you subtract 1, so f prime is this. So then delta y, change in y is going to be f prime of 25 times 2, which is basically 1 over the square, so 1 over 5, this guy right here, right? Okay, let's try another one. Let's keep going. So then we can approximate the square root of 27 is going to be approximately the square root of 25 plus the change in y. So then approximately this. That's interesting. I'm going to leave this as an exercise. Let's try, okay, we got a definition. So for y equal f of x, we define dx to be the differential of x by dx is equal to the change in x, right? So the differential of x is going to be essentially the change in x. And the differential dy, which is our differential of y, is going to be f prime times dx. So with these, I'm probably going to work these a little bit different than the way the book does it. I'm a fan, this is like implicit differentiation. I'll just do it the way that I'm a fan of doing it, and then you just kind of, and you can either do it the way the book does it or do the way I do it. I think you kind of need both techniques. Like the way I do it, it comes in handy often, but then it's like sometimes the way the book does it is easier. So I'm just going to do it the way that I'm comfortable doing it. I'll let you kind of research the way the book does it, and then decide which technique you want to use. But my recommendation is be comfortable using both techniques. So for instance, let's see it in action. So for this function, find dy, and then find dy when x is this and dx is 0.2. Okay. So I'm going to do implicit differentiation, and like the way I remember doing it, basically whenever we like we're gonna differentiate, but whenever like we take the derivative of x, we're gonna put dx, And whenever we take the derivative of y, we're going to put dy, right? So for part A, I think I might need some more space, so let me give myself some space. Let's add a page here, like this. Let me get a copy. I don't need this. Let's get a copy here. Hope everyone is doing well. We are rapidly approaching the end of the semester. It'll be here before you know it. I need to go ahead and update you guys' grades. I think this actually might be enough space, so I'm not going to do a certain thing. Okay. So now, for part A, we're given y equals x times 4 minus x cubed. Well, I was about to expand it, but then I don't feel like expanding that cube function. So I'm going to use the product rule for differentiation. But again, remember, whenever I take the derivative, I'm going to put dy and dx, right? So instead of just going straight to dy by dx, I'm going to do it a little bit different. So then now when we take the derivative of y is going to be dy. Now we're going to use the product rule. So it's going to be the first times the derivative of the second is going to be 3 times 4 minus x squared times negative 1, and we're going to put times dx. I think that's how that goes. So the first times the derivative of the second plus the second times the derivative of the first derivative of x is 1, I'm going to say dx, right? Okay, I could factor out dx from both of these terms. Actually, is that what we want? Yeah, let's just go ahead and do that. So then dy is going to be, and I'm going to kind of expand, and let me see. We can actually factor out 4 minus x squared dx. Let me highlight what I'm factoring out, because they both have this and that, partial there, and this. Style like this, right? So if we factor out, let me see, we have the 4 minus x squared. Okay, what's left? In the first term, looks like we have a negative 3x. In the second term, it looks like we have a 4 minus x. And I think what's left is the dx. I like you put that on the back end, on the back side, right? And let's go a little bit further. So then dy is going to be 4 minus x squared. That's a negative 4x. Here, let's write it. Let's write it like this. It's going to be 4 minus 4x dx. And we're asked to find dy. Yep. Okay. So again, all we did, we just differentiated like normal, but whenever we took a derivative, we put either dx or dy, and we treated the dx or dy like a term, right? And then we factored out the dx and kind of got like this result, right? So then part B asks us to find dy when x is that and dx is that, okay. So then part B, dy is going to be, x is what, 5? So there's going to be 4 minus 5 squared, 4 minus 4 times 5, and dx was 0.2. Okay. Let's go ahead and simplify. That's going to be a 1, so I'm just going to say that this term goes to 1. Okay. 4 minus what, 20 is negative 16. So it looks like it's negative 16 times 0.2. So negative 3.2. Okay. Let's see, how do we do? Let's compare to the notes. Negative 3.2 is good. dy, you see it right there. And we could have factored out that negative 4. I noticed it kind of towards the end, but what we have is essentially the same thing. You see it here. dy equals this. And then I think we got the same result with a certain x and a certain y. Okay. Let me see my time. I think we're looking pretty good. So then let y equal f of x be differentiable at some x equals a, at some a value. The linearization of f at x equals a is given by this. So this is going to be the equation of the tangent line of f at x equals a. So remember, our derivative is giving us the slope of the tangent line at a point. So then suppose we just wanted to jump straight to the equation of the line, the equation of the tangent line at a point. So if we want the equation of a tangent line at a point, let me see. If we were to solve, let me think about this for a moment. So y equals mx plus b, right? So this looks like point slope, right? Y minus y1. So it looks like this comes out of the point slope formula because this is our slope of the tangent line at a point. X minus that point, and then this is that y. Yeah, this comes out of the point slope formula from college algebra, where f prime is going to be the slope of the tangent line. Okay. Okay. So we're going to be using, this is called the linearization of f at x equals a. When we want to jump straight to the equation of a line, the tangent line at a point x equals a. So find the linearization of this when a is 27 and then use it to approximate this. Okay. Let me give myself some space. Okay. Like that is good. I'm going to go like this. We can just go ahead and maximize that. Okay. So that formula, let me see. So the equation of line, it comes out of point slope. I'm just trying to do it from memory. So y minus y1 instead of y1, we're going to do f of a. So there was an f of a there. Okay, plus the slope, which is f prime of a times x minus a. Okay, that should be the formula that was on the previous slide. Okay, so then we have this f of x, cube root of x. Let's go ahead and find f prime. So that's going to be d by dx of x to the power of 1/3. So now we can take the derivative. So then f prime, the 1/3 comes down, x to the negative 2/3. Okay. Find the linearization of this and use it to approximate that. Okay. So then, let's see, y should be f of a. So then the cube root of 27 plus f prime of a, so that's going to be 1/3 times 27 to the power of a negative 2/3 times x minus 27. Okay, so this should give us the equation of a tangent line when x is 27. Okay, let's keep going. So let's see. Cube root of 27 is what, 3? So that's going to be 3. I'm going to rewrite this. That's going to be 1 over the cube root. The cube root of 27 is 3 squared is 9. So it looks like it's a 1 over 27. X minus 27. Cube root of 27 is 3. 3 squared is 9. 9 times 3 is 27. I'm going to go with this. Okay, if we distribute the 1 over 27 and combine like terms, we get 1 over 27 times x. So what, minus 1? So then we're going to say plus 2. We could check by looking at the graph. Let's kind of go with this. Let's paste. Now, we want to use this to approximate the cube root of 28. Let me think about it. So what if we let, I'm thinking let x be, what happens if we let x be 28? Let me see, I'm going to see what the notes did from here. Okay. So they got the, you see the 1 over 27. And right here, y equals 1 over 27 times x plus 2, or the linearization is this, okay? So to approximate the cube root of 28, we substitute x equals 28 into the linearization equation, okay? So yeah, that's what we're about to do. And 82 over 27. So then the cube root of 28 is going to be approximately this guy. Well, on a calculator, is you see, like if we plug it into our linearization formula, we get this result. If we plug cube root of 28 into our calculator, we get this result. It's pretty interesting. Okay, that was fun. So we have a brief summary. Wow, these short lectures, 30 minutes. Okay, a little over 30 minutes. So if C represents the cost of producing X items, then the marginal cost is its derivative, and it can be approximated by this X plus first term minus the X term. The cost to produce the X plus first term can be approximated by C of X plus its derivative. And then similar discussion for the revenue and profit. Okay. In general, profit is revenue minus cost, which you see here. In delta notation, the change in X is going to be X plus some change minus the original X. And ultimately, that's going to be H. H is basically a change in X. The change in Y is going to be f of X plus H minus f of X. For small values in the change of X, we have the change in Y over change in X can be approximated by the derivative. And then if we were to solve for the change in Y, so our delta Y can be approximated by the derivative times delta X. The differential of X, dx is equal to the change in X. So then dy can be the derivative times dx. In general, dy is approximately the change in y. Okay, for sufficiently small values of dx. Okay. Okay. Well, that was an adventure. So on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Peace.